Okay, hey, welcome to the IRTF open meeting. And everybody wake up, it's only Tuesday. So we've got lots more to go. I'm the IRTF chair, Allison Mankin. I think many of you have been here before. I'm hoping a bunch of you are new because of our ANRW experiment of having our research workshop during the IETF week. And I'm going to talk a little bit about that, but very warm welcome to those who are here for the first time. We hope you'll stay around. Okay. It would be nice if this actually worked properly. Okay, so first of all, the traditional showing of the note well. How many are seeing a note well for the first time? I'm hoping a few of you, no? Okay, a few. Okay. All right, so this is the reminder of the policies. IRTF uses the same policies as the IETF, and in particular, we have some specifics about disclosing your patent or patent applications or those that you know about. There's lots of information in the note well. And we also have policies about being kind to each other, not harassing each other. We have a code of conduct. We have a privacy policy, so all that information is there. And because of the fact that we have a prize that we give out here, there is a lot of photography during this session, and our photographer will pay attention to your red lanyard if you're wearing one. But we have a statement on that consent as well. I want to mention to my research group chairs, and I said see email, but I haven't sent the email yet. I'd like you to update your note wells with the note well that's in here. So I'll make sure that I've sent that to you so that you aren't using note wells from years ago. All right, so a reminder of what we do here. IRTF has actually been around as long as the IETF in some form because originally the internet was a research project. But its current incarnation is a group that is supervised by the Internet Architecture Board. The appointment of the chair is by that. And we look at longer term research issues. We have research groups that are parallel to working groups. We have a steering group that's parallel to the IESG, although it has fewer duties. And we have a small number of at-large members on that. An important thing is that in the groups that you're going to go to, the RGs that you're going to go to later or later in the week, there weren't any yesterday because of the research workshop, we don't do any standards. So documents that come out from us are experimental or informational. And if you've got questions about that, please talk to me. We're also developing some thoughts about a new track of documents from the IRTF that we'll be writing about in the near future. So today I'm just going to talk a little bit, and then we're going to have the Applied Network Research Prize talks, Maria Apostolaki and Panos Papadimitratos, and I'll introduce them when we get there. But I have a few comments about, a few more things about IRTF. So this is the list of all of our groups. Most of them are meeting, and the ones in red I have some comment about. You can see we have a wide range of topics. They get chartered, they update their charters, they meet, they have interim meetings. There's lots of interesting activity. The Quantum Internet Group is a proposed RG. We have an approach where once you have a new idea, it's pretty easy to get a proposed RG. You get 3 meetings, and then after the 3 meetings, we decide if you're going to be chartered as a full-fledged RG or not. And Quantum Internet hasn't actually had a meeting yet. We also have a research group that's in planning. It's not yet having a real meeting, it's having a side meeting. So we have a lot of things. I have a couple comments on news. So this Privacy Enhancements and Assessments Research, PAIR or PAIR-G, is having a planning meeting this evening. There's a mailing list for it, prg@irtf.org. I'd love for you to get involved in that. I have another slide about it. We've been looking in open searches to replace some co-chairs who stepped down in HRPC, the Human Rights Group, and Protocol Considerations and Network Management Research Group. HRPC, we will be appointing the second chair this week. NMRG, we're looking at a recharter. And so we're going to rethink a little bit and take a little bit longer to think about the people. But we've thanked them before, but we'll thank again people who've been chairs there. And we will be looking for a third co-chair for the Crypto Forum Research Group, also known as CypherG. So just there's some news on that. This is a little bit about PairG. I hope for it to work in a parallel fashion to CypherG. There's much great research on cryptographic privacy technology that is not much incorporated into our thinking here at the IETF. So we're going to try to specialize a group to work the way CypherG does to help assess and bring forward useful technology towards IETF that needs more privacy. It's also going to do assessments. So an example here, I've encouraged them to get involved early on in looking at the choices and the privacy assurances for the new working group on message layer security, because we know that a number of these message layer protocols have not done so well. So bringing privacy expertise there sooner is better. And then there's going to be some topics. I'm encouraging some work on differential privacy in this relation to operations, but there are others as well. So come to that planning meeting, contribute. This is a time when it's an opportunity for you. The DIN-RG or DIN-RG or DIN squared Distributed Internet Infrastructure Proposed Research Group is having its third meeting this time. They've been having a lively charter revision with lots of discussion on their mailing list. They have a meeting Friday. Again, since we couldn't meet Monday, we've got our RGs kind of stacked up in doubles and on Fridays, but this is going to be a very good one. They're making progress on an experimental consensus protocol and also talking about a number of the aspects of centralization and decentralization and that are still really not well understood in our community. We've made a bunch of tries at it, but so Melinda and Dirk are the chairs of that, and I want to encourage you, and also we'll get your opinions about the transition from proposed to full-fledged. We had ANRW 2018. Thank you for the people who were there for being with us. It was a great day yesterday with tremendous credit due to Sharon Goldberg and Matt Ford for their efforts, and also all the speakers, the TPC, the other co-chair Dave, who didn't attend because of a paternity. Those of you who came for that and are here, welcome. I've said that before. Hopefully you'll do this again. We had about 100 people who registered. I took a poll of the room, and about 2/3 are here for the week of the people who were there, who were new. And at times, because people were coming in and out, we had about 200 people in the room. And sponsors included majorly ISOC and ACM, and then Akamai, Comcast, and my company, Salesforce. And Matt, you want to raise your hand? If people know of someone who'd like to sponsor, Matt is our everything about ANRW, and he can help you with figuring out how to get the sponsorship to us. Because, hey, we already have the logo. We're ready to go for next year. Expect some even more ambitious plans for it for the coming year. And as far as joining in, some of you who were there yesterday will recognize that Mark Allman presented and listed himself as a reformed IETF native. We really want people who are reformed IETFers or not yet IETFers to join in all the different ways in the IRTF. And there's a bunch of different ways to contact us. And just FYI, we also have not FYI, most of the rest of the agenda is going to be about the ANRP awards. So ANRW is the workshop, ANRP is the best papers. And those we give out 2 per IETF. We have a committee for that. We have different sponsors for that, Comcast, NBC Universal, and Internet Society. Because of our sponsorships, we can bring the awardees for an IETF week. And also we've been able to bring back some people who were awarded in the past. So I want to mention that Roya Insafi, who came to the Argentina IETF, is back for a return visit and will also be speaking in HRPC. And Paul Emmerich, who was, I believe last time, is back, and he is on the agenda in the benchmarking working group. We're happy to have the returnees, and people who are here might return, so get to know them. Okay, all right, so we have these 2 talks. The first one is going to be Maria's talk. She's from ETH Zurich in Switzerland. It's hijacking Bitcoin and routing attacks on cryptocurrency. You want to come up and set up your machine, Maria? And the second awardee is Panos' talk. That'll be about scalable security topics in vehicular communication. So let's get on with this. Here's this, and I'll get that one out. There we go. And our speakers need to stay in the pink box, so forgive them for their constraints when they can't walk up and down the stage because of our participants. We've got 9 participants on Meet Echo, so you actually have a real audience out there. Yeah. Mm-hmm. May not be on yet. Let's turn it on. There's a switch on top of it. You wanted to hold it.
No, it's okay.
Hello? Yeah.
Okay. So, hello everyone. My name is Maria Postolaki, and I'm a PhD student at ETH. I would like to thank you all for this opportunity that you give me to present my work on such a diverse and knowledgeable audience. So, today I will present our work on routing attacks in Bitcoin. This is joint work with my professor, Laurent van Bever, and Aviv Zohar, who is also a professor at the Hebrew University. Routing attacks quite often make the news. You will have probably heard about this Russian ISP that hijack large chunks of internet traffic destined to MasterCard, Visa, and other financial services. Or about this other Canadian ISP that managed to steal $83,000 by hijacking the prefixes of a mining pool. And the price just gets higher. Recently, like a month ago, there was an additional attack against my Ether wallet that also cost multiple thousands of dollars. However, this is only the tip of the iceberg in routing manipulations. By analyzing 6 months of BGP advertisement, we actually found that BGP hijacks are much more prevalent in the internet than we might have thought. So to give you an intuition of our findings, in this slide you can see the number of monthly hijacks that we detected in each of the months that you see in the x-axis. So you can see that there are thousands of hijacks every month. Of course, not all of them are malicious. In fact, most of them are misconfigurations. However, they are practical and they do affect internet today. The purpose of our work is to shed light on the impact of routing attacks in Bitcoin. Bitcoin should be robust against routing attacks, right? After all, it's a highly decentralized protocol of nodes that are scattered around the globe. They establish random connections, and they often use multi-homing and additional relay networks to interconnect. Unlike intuition, though, Bitcoin is highly centralized from both the routing and the mining viewpoint. To give you an intuition of our findings, in this graph, you can see the cumulative percentage of mining power as a function of networks hosting it. You can imagine mining power as computational power and networks as simple ISPs like AT&T. You'll see that mining power is very centralized to only few networks. For example, 10 ISPs host 68% of mining power. And it's not only about mining power. Even regular Bitcoin clients, they're centralized. For example, we can see that 13 ISPs host 30% of the Bitcoin clients. And to understand how scary this is, everyone can run a Bitcoin client. It doesn't require too much CPU. It doesn't require specialized hardware. And then if we look at the actual Bitcoin traffic, the things get worse. We found that in this graph, you can see the cumulative percentage of connection as a function of the transit networks intercepting it. And you will see that only three ISPs intercept 63% of the Bitcoin traffic. Because of all this centralization, two attacks are in fact practical and effective today. The partition attack, in which the attack tries to partition the network into half, and the delay attack, in which the attacker tries to delay the block propagation. The partition attack is very visible, and that's because the attacker needs to first hijack traffic. But it's also very effective, even against the Bitcoin network as a whole. The delay attack is extremely invisible, as the attacker only acts on traffic she naturally intercepts. But it's also effective against a couple of nodes, targeted nodes. So my talk today would be composed of 4 parts. I'll first give you some background information. Then I'll talk about each of the 2 attacks that we consider in our work. And I'll finish the talk with countermeasures, including our follow-up work. So let's jump to the background. Bitcoin is a distributed network of nodes that establish random connections to each other. Each of the nodes keep a ledger of all transactions ever done in Bitcoin. This ledger we call the blockchain. The blockchain is just a chain of blocks, and blocks are composed by, basically contain transactions. The blockchain is exchanged by miners, and miners have to use a lot of computational power to extend this blockchain, and they're compensated for this effort with block rewards, Bitcoins. Mining is a very risky process. You can mine for years and years and still not get anything. So what miners do is that they collaborate, forming mining pools. And mining pools need to also use regular Bitcoin clients in order to interconnect with the rest of the network. These special Bitcoin clients we call gateways. And they're often hosted in multiple ASs, in which case we say that the pool is multi-homed. For example, this gray pool has 2 gateways, node C and node E, and these are hosted in 2 networks. So this gray pool is actually multi-homed. Bitcoin traffic is routed by the internet. And the internet, as we all know, is composed of smaller networks, which we call autonomous systems. BGP is responsible for computing the forwarding path across them. There is a lot of traffic in Bitcoin, and this because it's a gossiping protocol, basically. But all this traffic is unencrypted, and it doesn't even have any integrity guarantees. That's scary, because any AS in the AS path can eavesdrop, drop, delay, or even modify the messages that are exchanged. I'll now talk about the first out of the 2 attacks that we consider in the paper. This is called the partition attack. The goal of the partition attack is to split the network into 2 disjoint components such that no information can be exchanged between them. If I had to describe why this is worrying with 1 sentence, I would tell you, well, Bitcoin is a consensus protocol. It cannot work if nodes cannot talk to each other. But now I have more time, I'll be more concise, and I'll tell you that it's an effective denial of service attack, as transactions cannot be moved from one component to the other. Second, it can cause revenue loss, and that's because all blocks that are mined within one of the 2 components, the one with the least mining power, will be discarded. And by discarded, I mean that all the miners that use their mining power to mine these new blocks they will lose their revenue. And finally, it allows double spending attacks. So basically, I can use my same Bitcoins to buy twice as much as I would regularly buy, just because I spent them in the different components. So now that I hope I persuade you this is bad, I'll tell you how it works. So let's assume we have this Bitcoin network, and this AES in the middle is malicious and wants to partition it to two disjoint components. Intuitively, what the attacker will do is attract all traffic destined to nodes in the right and drop all connections that cross the partition. To understand how this is done, we'll focus on one node, node F, which is the green node in the right end of the slide. And we'll explain how the attacker will use BGP hijacking to isolate this node. I do understand that many of the folks here would be bored with the next seconds, but I think it's important to engage everyone in the room. So basically, this node, node F, has an IP, and this IP belongs to its provider, so AES6. AES6 is responsible for creating this BGP advertisement that will be propagated AES by AES until all of them knows how to reach AES6. For example, AES1 will reach AES6 via AES7. The problem with BGP that you will hear many times in this meeting is that it doesn't check the validity of advertisements. And that actually means that any AES can advertise any prefix. So let's assume that the attacker actually advertises a prefix that covers the IP of the green node, and it's in fact a longer prefix than the benign advertisement. Because routers in the internet would route traffic based on the longest prefix match, everyone would choose to route their traffic via the attacker. And that's what we call the BGP hijack. And that's exactly what the attacker will use to partition the Bitcoin network. So he will hijack all traffic pertaining to nodes in the right, all prefixes pertaining to nodes in the right. She would drop the connections crossing the partition, and boom, the partition is created. Okay, of course, this is not as trivial as I just described, and that's because they're basically partitions that are infeasible to be created, and that's because they're connections that the attacker cannot cut. We have mainly three categories of such connections. Connections within an AES, and this an attacker cannot intercept because within an AES we don't use BGP. And also connections within a mining pool and private connections between mining pools. The reason why the attacker cannot intercept those connections is that she might be not aware of the exact topology within a mining pool, or she might not be aware of the exact protocol that the two different pools are talking. So it's harder for her to know what to hijack, and it's also harder for her to distinguish this traffic. But even in these cases, the attacker can detect that the partition she tries to create is infeasible, and instead create a smaller but feasible one. I'll give you an intuition of how this works. So let's assume that the same attacker wants to create a different partition, so the one that is denoted by this red line. We also assume the presence of a mining pool in the topology. And the attacker will again hijack all nodes in the right, so all the orange nodes. She will cut the connection crossing the partition, and the partition is created, but it's not effective. And it's not effective because the attacker failed to cut one connection, one stealth connection, but that was a connection within a mining pool. But what the attacker, in fact, this partition was infeasible to be created because the attacker could not know that this is a connection there. But what the attacker can do is that she can monitor the traffic she already hijacked and realize that the partition that she's trying to create is not effective. And it's not effective because the attacker can see leakage of information from one component to the other. So, for example, the attacker might notice that there was a block that was bound by black nodes and was advertised by the orange ones. And in fact, the attacker can even identify this one node that started the advertisement, which is the one node that actually had the stealth connection to the other component. And once she finds that, in this case, it's the node E, she can remove it from the partition and create a similar one that is, though, feasible. In the paper, we explained the exact algorithm that the attacker will use to do this, and we also proved that using this algorithm, the attacker will always be able to isolate the maximum feasible subset of nodes he initially wanted to isolate. We evaluated our attack in terms of practicality and time effectiveness. To evaluate the practicality of our attack, we had to infer the Bitcoin topology, which we augmented with routing information. Using this, we found that it's possible to partition the network into two disjoint components by hijacking 100 prefixes. And splitting the network to half is the worst case scenario for Bitcoin. Of course, hijacking 100 prefixes is negligible compared to the hijacks that happen often in the internet. And as an illustration, this graph shows you the maximum number of prefixes that were hijacked at once in each of the months that you see in the x-axis. So you can see that hijacks of 1,000 prefixes happen often in the internet, and 1,000 is one order of magnitude more prefixes that the attacker would need to split the network to half. We also evaluated our attack in terms of time efficiency. And to do that, we had no other option than do it in practice. But we attacked our own nodes, so no worries. So we host a bunch of Bitcoin clients at ETH. These clients were connected to the live Bitcoin network, and we advertised their prefix via Amsterdam. As such, all traffic destined to our nodes was routed via Amsterdam. Then we attacked our nodes by hijacking their prefix via Cornell, by another BGP in Cornell. And we measured the time it takes for all connections to be redirected to the attacker's network. This time is the same as the time that the attacker would need to create the partition. In this graph, you can see the summary of our results. So you see the cumulative percentage of connections that were intercepted by the attacker as a function of the time this took. So it will take less than 10 seconds for the attacker to intercept all the connections. That means that it will take less than 100 seconds for the partition to be created. On the other hand, though, a partition, like a hijack, will take a couple of hours to be mitigated. And that's because it's a human-driven process. And I'm sure many of you would have dealt with such a situation and understand how weird and difficult that is. It took even Google a couple of hours to resolve the famous BGP hijack, the Pakistan hijack. On the other hand, though, after the attack has been, after the hijack has been mitigated, the Bitcoin network is able to reconnect extremely quickly, in seconds. And that's because the network has a natural churn. So there will be new clients that will connect to the other component and that will quickly breach the partition. They will remain loosely connected, but that will not affect the consensus that much. And with this, I told you everything that I wanted to say about the partition attack, and I wanted to have a joke, but I failed. So yeah, I'll just talk to you about the delay attack. So the delay attack, the goal of the delay attack is to keep the victim uninformed of the latest mined block. And this is worrying for multiple reasons. An uninformed merchant is susceptible to double spending attacks because they don't know that certain bitcoins have been spent already. An uninformed mining pool is destined to waste its mining power, mining on something that is destined to be discarded. And an uninformed regular node cannot simply help in the peer-to-peer network. So let's see how it works. In this slide, you'll see 3 Bitcoin clients. Nodes A and B are connected to the victim. And we also assume the presence of an attacker that intercepts the connection between node A and the victim. Now let's assume that a block is mined in the Bitcoin network. Nodes A and B learn about it and they advertise it to the victim. The victim will request the block from the first node that advertised it to it. So it will request it using a get data message from node A. Now, if the attacker wants to prevent node A from getting this block, she can drop the get data message. Or when the block is delivered, she can drop the block. Both of these attacks, though, would fail, and that's because TCP would quickly disconnect, will abort the connection if certain packets cannot get through. What the attacker can do, though, is change the content of the get data message and make it look as if it requests for a different block, an older block. In this case, node A would actually deliver this block happily, and the victim will ignore it. And it will, in fact, wait for 20 minutes until it requests it from another Bitcoin node. So far, the attacker managed to keep the victim uninformed for 20 minutes. And that's a lot of time for a Bitcoin client because blocks are mined in expectation every 10 minutes. And so far, the attacker managed to do this, and if she doesn't do anything else, what the victim will do is that after the 20 minutes timeout, will consider node A as malicious and will disconnect. But if the attacker actually wants to avoid it, to avoid detection, or to keep it, because she wants to keep the connection, what she can do is the reverse operation. So she will again change a get data message such that it requests for the initial block. If the block is delivered within the 20 minutes timeout, the victim will not consider this whole process as malicious, will keep the connection and will be happy. So the attack is completely under the radar. The reason why we actually use a gate 8 alpha transaction is that those are many more. So it's more likely that the attacker will find one such message. We evaluated our attack in terms of effectiveness and practicality. To evaluate the effectiveness of our attack, we had to perform it in the wild. So we again used the Bitcoin nodes that we hosted at ETH, were connected to the live Bitcoin network, and we assumed the presence of an attacker that could intercept a particular percentage of the victim's connections. Using this setup, we found that an attacker can keep the victim uninformed for most of its uptime. And that's even true if the attacker intercepts only a fraction of its connections. To give you an intuition of our findings, if the attacker intercepts 50% of the victim's connections, she can keep the victim uninformed for 63% of its uptime. And if you think that doesn't happen often, let me tell you that for almost 70% of the Bitcoin clients in the internet, there is such an ISP that intercepts 50% of the connections that the Bitcoin client can create. And with this, I'll talk to you about countermeasures. Luckily, countermeasures for both attacks are possible. For example, we can easily deal with delay attacks if we adopt an encryption in the Bitcoin protocol, or if at least we include some kind of MAC in each packet, such that we are sure of the integrity of our packets. This way, the attacker will no longer be able to modify the packets until, at least without the receiver noticing it. An easier countermeasure would be to let the Bitcoin clients be more smart in the way that they select their peers. So to select their peers in a more routing-aware manner, such that there is not a single ISP that intercepts most of its connections. However, dealing with partition attack is more challenging. The easiest way to do it is to actually host all our Bitcoin clients in /24. This would be an effective countermeasure because it would force the attacker to actually advertise the same prefix as the origin, as the benign origin. And using this, the attacker will only be able to attract half of the connections she would normally attract. She would attract if she was using a longer prefix advertisement. A better way to deal with this problem is to actually deploy secure routing protocols. Of course, yes. Because this would help us in not actually having hijacks at all. And I see some smiley faces, but most of you are concerned. And I understand that. So what you're thinking is that's not practical. And I actually totally agree. okay, we cannot host all our Bitcoin clients in /24 because that will increase our routing tables. And yes, deploying secure routing protocols would be awesome, but yeah, we're not there yet. And we will not be there just because of Bitcoin. So what we envision and what we're actually working on is to create an additional secure channel that will be able to let our clients, let Bitcoin clients exchange blocks even if their network is partitioned. So even if there is a BGP hijack that is going on. And we built this system that we call Saber. And Saber is basically a relay network. So that means that there are few special Bitcoin clients that connect to each other and also connect to all other Bitcoin nodes. So as an illustration, if we have this Bitcoin topology, Saber will look like this. It will be some additional Bitcoin clients that connect to each other and also connect to the rest of the Bitcoin clients in a way such that the Bitcoin clients don't need to talk directly to each other, but they can talk via the secure channel, so via Saber. Now let me tell you what is special about our relay nodes or Saber nodes. So first, they're strategically located in the internet such that the chances that the attacker will be able to hijack the connections between the relay nodes or between the relay nodes and the actual Bitcoin clients is minimal. And second, they're implemented in a way such that they're robust against denial of service attacks. So let me tell you first how we position our relay networks such that we secure them against hijacks. So first, we make sure that our relay networks are hosted in /24 prefixes. And that's crucial because we will force the attacker to advertise the same prefix as the benign origin. So it will be in competition with the advertisement. Let's zoom a little bit more on that. So that's an AES topology, and the arrows that you see would show the money flow. So for example, the topmost AESs are the provider of the middle AES, and the middle AESs peer with each other. And then the bottom AESs will be the customers of the middle AES. So now let's assume that the middle AES is an attacker and she hijacks a prefix of the blue AES that is labeled as origin, and she actually uses the same prefix advertisement. So all the AESs in the slide will learn about these two advertisements and they will have to choose between them. This decision is taken based on two factors. First, what is their business relationship to the attacker and to the origin? And second, how close they are to the attacker and to the origin. So basically, this is what will happen. The red AESs that you see would be those that will be lured by the attacker's advertisement. So they will be vulnerable to this attack. For example, the providers of the attacker would happily follow the attacker's advertisement, and that's because they don't have to pay for it. And the peer that is directly connected to the attacker would prefer the attacker's advertisement because it thinks it's closer to the actual destination than the origin. However, we also see these green AESs, and these are the AESs that are not vulnerable to this attack. For example, the customers of the attacker will not be willing to pay for her advertisement, so they will not be vulnerable to her attack. All this to say that as our relay nodes are already hosted in /24, the one crucial thing is what is the relations to the other AESs that host relay nodes, as well as to the AESs that host Bitcoin clients. So we add a requirement while we place the relays, and that's that we'll only place relays in AESs that peer directly to each other and also have no customers. What this would buy us is that we will be sure that it's not possible for the attacker to advertise something that looks better to the AESs, that is more preferred. So it will look roughly like this. We have these two relay nodes. They are in AESs that peer directly to each other, and they're in AESs that have no customers. However, we do know that peering connections might be revoked, the peering agreement might break, or the link might fail. If this happens, then our relay node would be disconnected, and that's bad for Sabre because then we cannot guarantee anything. The way we deal with this problem is that we require, while we choose the location of our relay nodes, that the graph that the relay nodes would compose is K-connected. That means that the attacker would need to cut at least K peering links to be able to disconnect our relay network. Okay, so going back to the example, we would need to add one relay network, one relay node that will be hosted in AES that peer directly to the AESs that already have relay nodes. As such, if we lose one of the links, we will still be fine because the relay network would still be connected. And the last thing we take into consideration while we place our relay nodes is that we eliminate the chance that an attacker would be able to hijack traffic from the Bitcoin clients to the relay nodes. So I'll explain that with an example. Let's assume we have this AES topology and we have two Bitcoin clients that we want to somehow protect. And the way we do, and we're trying to find an AES to host a relay to protect those clients such that there is no attacker that can basically hijack traffic from the AESs with Bitcoin clients to the relay. So let's assume we place the relay there. And what will happen in this case is that we'll have two possible attackers. So these attackers, for example, the attacker that is in the middle would be able to hijack the prefix of the relay by advertising it to the AESs with Bitcoin clients. And those AESs would actually follow the attacker's advertisement because it's their customer, so it's more preferred path. However, if we face the same problem and we place the relay in this AES, then we would have no attackers. So this is what we try to leverage while we're placing our relay nodes. Okay. I'll now tell you how Sabre will help us in the partition attack that I described before. So let's assume we have this Bitcoin topology, and as we described, if we have an attacker that hijacks traffic and we not have any countermeasures, then the attacker will be able to create this partition. However, if we deploy Sabre, then we would actually have these additional Bitcoin clients. They will be hosted in AESs that peer directly to each other, and they will be connected to the other Bitcoin clients. And if there is an attack that happens, and if we assume that the attacker even hijacks more, so she hijacks even the prefixes of the relay network, she will manage to cut some connections, but the actual Bitcoin network would still be secure and connected because of all the properties that I described before. And now let me talk to you about the second guarantee that we offer, and that's that Sabre offers, and that's the special way that we implement Sabre nodes such that they're better with respect to denial of service attacks. So they can remain open to new connections even if they are under high demand or even if they're under a DDoS attack. So we use a software and hardware co-design. So we have a hardware component and a software component, and the software component is only responsible for validating the block and for updating the hardware component with the new mined block. The hardware component is actually programmable switch, and you might have heard of this Tofino and this P4 language that we can program our switches with. And we're basically, the switch is now responsible for answering to all the requests of the Bitcoin client. So in a way, you can imagine that the switch actually talks Bitcoin. The reason why we believe this design is suitable for our problem is twofold. So first, it can keep up with high demand, and that's because the programmable hardware is supposed to be able to keep up with terabits of traffic per second and process them at line rate. So it can sustain large denial of service attack and also high demand. And the second reason why I believe that this design is suitable is that it allows us, so the programmable hardware allows us to have dynamic network defenses in the switch. So, for example, Sabre nodes would have whitelists and blacklists and some spoofing detection, and also some detection to be able to avoid being used as an amplifier. And now let me tell you why this co-design is possible, because that's not that trivial, as switches are not like for everything. They have few computation that they can do. And that's because Bitcoin is a very communication-heavy protocol as opposed to a computational-heavy protocol. So basically, there are more messages exchanged, there are more I/O that is used than actual computation. And the second reason why our design is possible is that the caching mechanism is very efficient, as the blocks that we actually cache in the switch, they're only updated every 10 minutes. Okay, and now that I have described the Sabre nodes, we will go through the life cycle of a block. So in this slide, you basically see two Sabre nodes. They're connected to each other, and they're also connected to the Bitcoin client, to some Bitcoin clients. And now let's assume that there is this block that is mined by a Bitcoin client. This Bitcoin client would notify the switch about this new block. The switch will realize that this is a new block in the blockchain. It doesn't know about it and will notify the controller. The controller will be now responsible to validate the block, so to check whether this block is correct. If the block is valid, the controller will update the cache in the switch such that the switch is now able to answer to all the clients that will request for the block. So the switch is now responsible for basically propagating this to the other Bitcoin clients and to the other Sabre nodes. And with this, I finished my talk. If you were to remember one thing from it, it should be that Bitcoin is vulnerable against routing attacks from both the network and the node level. The potential impact of these attacks in the currency are worrying, because they're an effective denial of service attack. They allow double spending, and also they can cause lost revenue. And finally, countermeasures exist, with secure routing protocols being the best and Sabre being a good alternative. Thank you. I'm happy to take questions.
So say your name when you give your question.
Hi, I'm Kathy Aronson. I think it's somewhat unlikely that an AS would have no customers, but you could also use an AS that perhaps does what the BCP says and filters what its clients announce to it. Then you would have the same, because a AS not necessarily having customers is, anyway, but if they filter what their customers advertise to them, then their customers can't advertise something that doesn't belong to them.
Like one answer to this is basically that by having direct peer connections, we also avoid the passive attackers that are in the middle. And what we also need to think about is that, yes, we might find, that's very good, and actually that's very good to create an incentive for ISPs to actually filter, but you have to take into consideration that we need to find those locations such that they're also close to the Bitcoin clients. Right. So the more of we have a lot of ASs that actually peer to each other, but I don't think that we have that many ASs that filter or that we can guarantee about that.
But they should be.
There should be. I totally agree with that.
Hi, thank you for report. My name is Alexander Azimov. Can you go back to the picture with car route peerings?
Describe what?
With peering interconnections for Sabre.
With peering connections.
There was 3 nodes.
This one or before?
Yes. Yes, this one. Do you assume that if there is a direct connection between relay 2 and relay 1 and relay 2 is broken, do you assume that the traffic will go through relay 3?
So the point of that is that the relays will compose a graph that is always connected. So if one link is broken, I don't want to use an alternative link that will basically connect the same relays, but I want to transfer the information via another one.
According to the regular peering connections, if you have traffic that goes not through IP address of relay 3, but goes directly from relay 2 and relay 1, they will send it. They will send traffic through upstream providers. Because if we're speaking about peering connections are exchanging routes that belong to themselves and to their customer code. Here you don't have customer code. So relay 1 and 2 will not exchange prefixes that belong to relay 3. Otherwise, it's a route leak.
Sure, but the only reason that I need the peering connections are that basically I avoid okay, so let's assume that there is okay, I have no, that's hard because I got okay. So I'm not sure I understand the question, because the reason why we actually need the peering links is because nobody can advertise to relay 2, for example, the prefix of relay 1 and be strictly more preferred.
Yes, until they are connected.
Sorry?
Yes, until they are directly connected.
Yes.
Is the peering link
If they're not directly connected, so if the link is broken, then I'm not using this link at all. So I will not try to transfer information from relay 1 to relay 2. And this is why I need the relay network to be always connected, because I have an alternative route that is composed of direct peering links between among the relay nodes.
So you're speaking about route, you're speaking here not about BGP route, but speaking about some logical overlay network that is built upon the relays. Am I right? Because you will not have
the relays
BGP
are
route.
actually the relay network. It's not, there's not an additional network on top of them. But what I want to say is that, so do we agree that if the relay nodes are connected with peering links and they're at least K connected, let's say 2 connected, then if we lose one peering link, because of any reasons, because like it can go within any path, then the information can be exchanged still via the links we have.
Only via proxy.
Only?
Only using some kind of proxy.
But it is a connected network. The proxy that you're describing is basically the alternative path.
The peering links are not exchanging routes that belong to other peers.
But the other relays...
There is a physical connection, but there is no logical connection. Inside BGP, there will be no such route. Okay, let's speak after there is a line. And so
this seems like something the whiteboard might be necessary for. So why don't you find each other later? Yeah.
Hi, Phil Baker. I'm going to make myself unpopular here. I think that if you go to your last slide, I'm not at all worried about attacks on cryptocurrencies. I mean, Bitcoin is using as much net electricity as Nigeria. Bitcoin is an attack on our planet. It's an attack on our financial infrastructure. And I don't want to see people improving Bitcoin. I want to see better attacks. And I'm absolutely serious. Better attacks on Bitcoin. The sooner we sink it, the better. Think of the planet. I'm absolutely serious here. We have an abomination that is using a vast amount of electricity to transfer an infinitesimal amount of money. It is convincing people that they're making money in their basement, and it isn't, of course. It's got trillions of dollars that is magicked out of nowhere that is going to crash. It is an attack on our financial infrastructure. So please, don't think of this in the normal academic fashion of, this is an attack, I've got to find a defense for it. This is an attack. Here's how to make it better. So
I want to add 2 things on that. So first, the work is about attacks on Bitcoin, so you would be happy. But I will only talk about the environmental part. And I want to let you know that there are actually data centers in San Jose that are using more, they're using actual water for cooling the data center. And they're using more water than people can use in San Jose. So, of course, there are inefficiencies. And of course, we're really bad to our environment, and it will kick us back. But it's not about the blockchain. That's like a general problem.
All right. My name is Shane Kern. I'll try to be less hyperbolic. Have you thought about the financial model of how you're going to maintain these Sabre nodes? Do you intend to, I don't know, how do you expect to pay for this in the long run?
First I want to let you know that there are already relay nodes that everyone can connect to, and they're mostly maintained by academics, or they're supported by academics. But our intuition is that it would be very nice if an ISP would deploy it, because it would prove that it is in such connection, in such position in the internet, that it can actually help Bitcoin. So I believe that would be kind of an advertisement. Plus, if we implement it using these programmable switches, most likely they will already have this there. So they will already have the switch. They can have the switch and use it for other purposes. And then adding just a relay node is not too much. But I get your concern that this is problematic a little bit.
Yeah. And I'll ask one other question. Have you looked at what the possible impact of Lightning Network is going to have on this whole picture?
What do you mean?
So Lightning Network is a sort of change to the Bitcoin model, where instead of all peers connecting to all other peers, there's Lightning nodes, which act as a kind of localized network.
Okay. So if I get your question correctly, you're worried mostly about centralizing something that is destined to be decentralized, and that's bad, right?
Yes.
Yeah. So I totally agree with that. What you need to take into consideration is that we don't want to replace the Bitcoin network. We just want to provide an alternative.
Oh,
just in case there is an attack.
I wasn't clear. No, that's actually not what I was asking about. So I think the Bitcoin network, the model of how it's going to work in the future is changing. So there's scaling problems with the current network, and the approach taking to work on this is that when you do a transaction, it's not necessarily going to be broadcast across the whole network right away. You'll be working within limited domains, one or small number of Lightning nodes, and then at some point, those will go across the whole network. It has lower guarantees, but in order to scale it, it has to go that way. And I don't really know how your attacks fit in that, whether it becomes more or less secure, and how the Sabre solution actually fits in that picture.
I want to focus on one thing of what you said. So you said that at some point, be it every 10 minutes or be it every whatever time, they will need to exchange what they have done. Otherwise, it's not possible to have consensus among the Bitcoin clients, right?
Right.
So when this happened, if the network is partitioned, it would not be possible. So this applies.
Okay.
I'm not sure if it's worse.
No, I agree that that's always going to be a problem, but I'm not sure. I think it may be even worse than a Lightning Network scenario. So anyway, yeah.
Hi, Doug Montgomery. So to the extent that I understood your work here, right, you rely on placement of various nodes that are topologically aware. Do you address how you'll both learn about the AS topology and react to its changes?
So if I understood correctly your question, you're asking whether once I place them, I care about the changes that might happen.
How did you know the AS topology in the first place to place them?
So KAIDA has this database that we can use to infer the business relationship among the ASs. And yes, that's not perfect.
Tomorrow,
but
should KAIDA lose funding, does your system still work? So your system isn't self-aware. It can't discover the AS topology itself, nor react to it in any kind of dynamic fashion.
Sure, but every time you're in an AS and you want to know your AS path to another, you can always use a trace route. And it's just that it would require like more time if we were to start trace routes from everywhere instead of actually using the KIDA topology. But to answer to your question, if the system was in place, there should be also trace route to check whether, for example, there are changes in the paths, or such that we keep track with whatever happens in the path between the relays.
Okay, thanks.
Hi, Stuart Card, Critical Technologies, first time face-to-face IETF participant, been involved in the activities online for many years. First, a quick comment. I have been absolutely astonished in the past few days at the paucity of discussion here at IETF about the potential interactions between not just Bitcoin, but the broader blockchain and broader cryptocurrency, which should not be equated with each other, research communities and so on with IETF activities. I've been wandering from working group meeting to working group meeting, looking at important problems that have been studied for many years, to some of which there are obvious approaches involving the use of either blockchain and or cryptocurrency technology to address them. So I guess I would like to ask you a kind of a broad question, considering especially that things like the Bitcoin energy cost are well known within that community and are attempting to be addressed with proof of stake and other approaches. Do you have any ideas for broad areas of research in the intersection between cryptocurrency and blockchain technologies and IETF technologies, where we might invert the relationship rather than regarding Bitcoin as merely an application of our network, regarding cryptocurrency and blockchain technologies as potential enablers of our network?
So maybe that I might have a better ability to answer that. So Stuart, we actually have this DINRG, which is the home for this kind of research, Friday afternoon. So it's just that you've been wandering, Friday morning, you've been wandering too early. But I think we're aware, and that's one of the reasons this paper was so interesting to us, is because there are tremendous interactions. There's communities that need to intersect more. So that is sort of the place where we're hoping that intersection will flower especially.
Hi, Max Bala, Cable Labs. Have you considered the deployment of TLS among nodes, especially for pools or nodes that have lots of connections, so that would guarantee integrity and protection against all these attacks?
The problem with that is that we cannot really solve the partition attack with that. We can only deal with the problem that an AS level adversary can modify the messages that are exchanged.
That's true. Thank you.
Hi, Anshul Malhotra from Boston University. I have a question on the countermeasure that you said for delay attacks. You mentioned encryption and MAC as the potential solutions. I was wondering, how does that help against a man in the middle? The delay attacks, how does encryption or MAC defend against a man in the middle who can drop the packets?
So if a packet is dropped, the difference is that in this case, the Bitcoin client will notice and will request a block from another peer. The problem is that the node actually thinks that everything is working properly because it doesn't have the connection is not lost. So like when I was describing the attack, I said that the attacker can drop the get data message or drop the block itself, but this will make TCP basically disconnect, will abort. So the Bitcoin client will actually notice that. I'll find it. So here, if instead of modifying the message, the attacker drops the get data or the block itself, then TCP will keep the sequence numbers and will not be able to continue. So it would reset the connection or it will disconnect. Does that make sense, or was that what you asked?
Yes, it does, but it still is a delay attack. Like it still is delaying the delivery of the block. Not necessarily for 20 minutes maybe, but...
Sure, okay. Dropping is a problem and it's what will be used for a partition attack. But the key in this particular, in the delay attack, is that it's very invisible. So it's not possible for the node to actually understand that it's under attack. But you're perfectly right that even if the traffic is encrypted, it can be dropped, and so the network can be partitioned. This is why we consider encryption as a solution to the delay, but not to the partition attack. Thanks.
Hello, Bin Yang from Huawei. My question is that are the attacks and the countermeasures specific to cryptocurrency networks, or they are general to any peer-to-peer networks? I mean, the delay attack is specific to Bitcoin. I think Ethereum is not vulnerable to the delay attack, right? But for the partitioning attack, I think it is general to any peer-to-peer network. So how about the countermeasure? Is the countermeasure general to all the peer-to-peer network?
So I do believe that at least the cryptocurrencies would be vulnerable to a partition attack. What I know about Bitcoin that might be different to other cryptocurrencies that is more centralized. So it would be easier for an attacker to hijack this traffic. But you're perfectly right. Any peer-to-peer network would not be able to function if you basically split the network to half. Does that answer your question?
I mean, there are a lot of peer-to-peer networks, including Tor and the current cryptocurrency networks. So I mean, is your countermeasure to the cryptocurrency network still applicable to the general peer-to-peer network? Can your countermeasure protect all the peer-to-peer networks?
So if we assume that we study all the partition attacks in all the networks that you described, then yes, we can imagine that we can have a relay network for all. But like, I cannot comment on. So I do believe that it's a general approach that you want to build a relay network to help a peer-to-peer network. But I cannot comment on whether, first of all, such an attack would be feasible in something else, whether somebody would be interested, for example, to split the Tor relays using hijack.
Yeah.
I don't know about that. So if we assume that there is an attack model that would make sense with hijacking, then yes, somebody can use the same properties to build a network against this attack.
I think it may be more interesting if we can design a secure peer-to-peer network that is not vulnerable to the partitioning attack.
Sure, I totally agree with that.
Thank you very much.
Okay, and this will be the last question.
Hi, I'm Jim Fenton. One of the characteristics of the Bitcoin network that I think the Bitcoiners take a lot of pride in and sort of consider as a kind of fundamental thing is the egalitarian peer-to-peer nature of their nodes. And I'm wondering if you've gotten any feedback from that community about Saber, because that's a situation where now you're starting to create the beginnings of a hierarchy. Not all nodes are Saber nodes, and they don't have all have the same, are the Saber nodes considered perhaps a point of control, that sort of thing. Have you gotten any feedback on that?
So first, no, this is not work that has been published yet. I want to say two things though. First, there are already relay networks out there, and they're like basically used for a different reason, to improve the performance of the Bitcoin network. So you can assume that you have the same property there, that there are some nodes that are connected to them, and maybe we're kind of better to them. However, what I want to point out is that we envision a network that would be open to everyone and will not be controlled in a way that can do something bad to the Bitcoin, because even if it was controlled, it doesn't. The Bitcoin clients would still have their connections to each other, so it acts on top of that, and as such, it doesn't have the power to do something against them, I believe.
Okay, thank you.
Okay, well, thank the speaker. So I think I do remember to tell the speakers that that we get a very thorough set of questions from IETF, and that's one of the reasons to come here for ANRP. So our next speaker is going to talk about a paper that was published in a journal about secure vehicular networks. Let's see if I can get us back together here. And I need to put this back in also for you. Panos is on the faculty at KTH in Stockholm, and hopefully we haven't actually. Oh, I need to do this first. Wait, no. What? I'll do this now. Come on. This is exactly the configuration you were in before, and you worked. Why aren't you working now? Do I have anybody here who can advise why this is not working now when it worked before?
Somebody working
Huh?
Somebody working
Yeah. Here we go. Yeah, all right. So I think this should now work for you properly. Okay? So take it away, Panos.
All right, thank you, Alison. Alors, bonjour, merci bien pour cette opportunité. Ça me fait énormément plaisir de revenir à Montréal. So, shall I continue in French? No? No? Alors, ouais. Ouais, je pourrais essayer, mais des fois, c'est un peu difficile avec la terminologie, etc. On écrit tout en anglais. So, one way or another, I'm Panos Papadimitratos, and I'll be telling you about some of the work we have been doing on vehicular communication systems and their security. I have quite a lot of material in these slides. The major part is about the paper, but then I also have some, let's say, extensions or closely related areas of research so that we can expand a little bit the sphere of the discussion. So, I think maybe you need some sort of.
That is an interesting question. I think this is. See what happens now. Maybe.
Oops, no. Full screen.
I have
Control
it in full,
L.
wait.
Control L or something.
Oh, maybe I didn't get it all the way to full screen over here. Here, yeah, that's the problem. Sorry. Yep. Okay, that should do better.
All right. So. Yeah, I'll stay within the circle. It's a bit theatrical. If it was a drone with a piece of chalk, that would be even more spectacular. So the idea is we are concerned with this emerging type of systems, vehicular communication systems. The idea is that you add additional processing power and communication capabilities on those vehicles, which already have tons of computers on board, so that essentially, by providing this vehicle-to-vehicle or vehicle-to-roadside infrastructure communication, essentially you enhance transportation safety and transportation efficiency. So these yellow arcs you see, this is vehicle-to-vehicle communication, and then there's an arc with a node on a lamp post. Essentially, you extend the horizon of the driver, and either you use this to advise or warn the driver so that she takes the action, say hit the brake, or you can envision this system supporting autonomous driving down the road. Now, we are concerned with security and privacy. So let me take a there's a bit of latency here. Let me take a simple example here. Let's say that exactly this notion of extending the horizon of the driver is applied to warning about an approaching ambulance. You could have an application that your car collects these messages and lets you know exactly where the ambulance is coming from, rather than you trying to figure out where the siren is sounding from, and so on and so forth. So what you do is that you yield and then you let the ambulance go through. But you could imagine in the near future someone buying basically a hacked version of this application that essentially transforms his car into an ambulance, and then everyone else yields and he goes to work or to wherever faster than everyone else. So that's a motivating example, but essentially there could be even more dire consequences if you were to attack these vehicular communication systems. You could cause accidents, you could cause traffic jams, and so on and so forth. That's why you need security. And focusing on the communication part of the system, of course, you need to care about where messages come from, whether they were changed, whether someone can deny later on having sent a given set of messages, who is allowed to do what. Then being in a car defines where you are and can actually lead to your identification. In any ways, it can lead sensitive information about yourself. So you need some sort of protection of privacy, and I will get more into that soon. So you need some sort of anonymity, and the consensus is to go with conditional anonymity, meaning that you anonymize, nonetheless, you keep somewhere the long-term real identity of the entities involved, so that should there be some sort of accident or some emergency, you can pull it out. And then you need some sort of unlinkability, meaning if you're communicating frequently, you don't want these communications to be trivially linked to each other, because that could lead to some sort of de-anonymization in the end. Now, there has been some effort in this direction, and there is even developing standards. Now, what are the underlying ideas? And we have been involved in this since the very birth of the area. So what's the simple idea here? And I'm taking one type of application, what is called the cooperative awareness messages or safety beacons, those that basically let your car tell other cars how it's moving, so that basically can adjust and warn the drivers. And let's take the very simple way of providing security. Essentially, you have a digital signature, and you attach a certificate, and then everyone can validate your message, no matter what has been any prior association or knowledge, which clearly is not something you expect in a highway or in any road setting. Nonetheless, every time that you digitally sign a message, and these messages, they come very frequently. Typically, transportation engineering says that you need to transmit up to 10, or even in some occasions, even more than 10 per second. So essentially, and each of them tells exactly how you're moving, what's your location, what's your velocity. So the idea there is that every time you digitally sign messages, trivially, you allow anyone to verifiably link them, right? Even if you remove the identity, even if you made your credential an anonymized credential. So what could be a solution to fully anonymize this and make these unlinkable? Use some sort of anonymous authentication cryptographic primitive, which is quite expensive from a computation and communication point of view. So the consensus there was to take a trade-off. So essentially what we proposed was to leave with short-lived credentials, classic cryptography, public key cryptography. So the overheads that we all know and the algorithms we all know how to implement pretty well, and allow some partial short-term linkability of these communications. Why? Because it's also easier for transportation safety applications, for example, of collision avoidance notifications, to basically function in this way. There is, of course, the next step to blend anonymous authentication and classic public key cryptography, so that you can generate on the fly let's say credentials, but I won't have time to go into that. It's also not part of what is being standardized. Now, how do these boxes look like? I mean, on the left hand, or your right hand side, you see what was back in 2008 when we wrote the software for the security functionality in the first field demonstrations of such systems. And 7 years later, everything got a bit condensed, because anyways, you wouldn't buy a car that doesn't have any trunk space. I mean, of course, some people buy sports cars, but that's a different story. Essentially now you have a hardened box with a real-time Linux, with a dual-core CPU, et cetera, et cetera. And these are, let's say, what you call on-board units, and you have the antenna that sits on the top of the your car. And that's from a field operational testing. Just the devices are on a table there that I show you. Now, who provides these credentials that I have been talking about? These short-lived anonymized credentials that we call pseudonyms. Well, there is a public key infrastructure behind. And in this case, there is a set of entities. And here I show you domains. Essentially, that could be a state, a city, or even a car manufacturer that provides credentials for all vehicles registered in that domain. And there is a split. There is one entity, the long-term certification authority, which basically keeps track of the long-term identities of the vehicles and provides the corresponding certificates or certificate. There's one, and there is one registration per vehicle with one long-term certification authority. And there could be one or more pseudonym or certification authorities, those that provide the short-term anonymized credentials. And the idea is exactly that the vehicle runs and authenticates all communications with the short-term, the ephemeral credentials, the pseudonyms. Why? Because if it used the long-term one, then it would be trivially linked and privacy would be lost. And this slide basically says with texts what I just mentioned before. It also says that you can establish trust between different domains in different ways with cross-certification, with some higher level certification authorities. And should you really need to revoke the anonymity of the involved vehicles, then you need to have another authority that has the necessary, let's say, circumstances, the necessary authority to basically request for that information. Otherwise, this information is essentially split into the two entities, the long-term certification authority and the pseudonym certification authority. Now, talking about security and privacy, of course, the problem is more general. Now, I will gradually, let's say, focus on exactly what we looked at in this paper. There could be malicious behavior. The onboard units, the boxes I showed you earlier, they could basically be hacked by anyone, either remotely, as we have seen in the news, let's say the current counterparts of those systems, or one could basically alter the functionality of this, or one could even modify sensors on board, let's say other controllers on the cars to feed wrong information to those machines. One could also envision the possibility that you have a compromised vehicle, but then you try to make it look like as if you had 10 vehicles, or 20, or 100, or 1,000, right? Why? Because there could be all sorts of applications where if you could pose as multiple vehicles providing data responses to those applications, then you could dominate the outcome of the protocol, whatever is the protocol or the application you're running. For example, you could fake that there is a traffic jam, to put it very simply. And of course, you could have collusion between these adversaries. And now we are moving, let's say we're pushing the envelope one step further. We're thinking of the security infrastructure, the certification authorities, right? What if they are not fully trustworthy? What if they're honest but curious? Basically, they follow the protocol, but nonetheless, they try basically to extract information about the participants. And looking exactly at the provision of the credentials and the management, this vehicular public key infrastructure, as we call it, we care to address exactly this type of adversarial behavior. So we are not content with a fully trustworthy VPKI, but we want to deal with an honest but curious, or even gradually start moving towards dealing with some sort of deviant behavior from a entity within the VPKI. And in addition, we are dealing with the challenges that the system itself is bringing forth. So, in particular, there's this balancing act between security and privacy that I explained already. Then it's a complex deployment environment, and it becomes more complex because most likely security will be mandatory for all vehicles, let's say, that will be engaging in vehicle to vehicle or vehicle to infrastructure communication down the line. The credentials that we're using are short-lived, which means that every entity, rather than having one public-private key pair and one certificate, has thousands of those. And it keeps throughout the lifetime. And then, of course, there are cost constraints imposed, for example, by the car manufacturers. Right? We don't want to spend a fortune for that system on board. And we want to make sure that our VPKI provides credentials, can survive, can function actually properly, even as the system gets more complex and grows, in spite of all the constraints. And of course, we want it to be guaranteeing proper operation, in the sense that, especially in the sense of eradicating civil misbehavior. We don't want anyone to be able to interact with the VPKI, especially in this distributed setting where you have multiple providers of such credentials, and obtain many of those. How would it look like if we were to zoom a little more in zoom in the system? Well, let's look at two domains here. On pick one, let's say the home domain, where you have the home LTCA, and then the car essentially now submits a request to obtain a ticket that will allow it to address, that will provide it to any PCA and obtain credentials. What's the change in a system that probably reminds a little bit of Kerberos is that we want actually to disconnect or hide information from the LTCA regarding which PCA the vehicle is going to obtain the credentials from. We also want to hide the period for which it requests credentials, because these are sensitive pieces of information, right? And they could allow an honest but curious LTCA to track the vehicle and its activities. If, of course, the LTCA, the curious LTCA, the curious PCA also had transcripts, meaning logs of messages that the vehicle transmitted while it moved around. Would that latter be difficult? No, because all you need is some sort of variant of 8.11 for this vehicle-to-vehicle communication, and you can record all such traffic easily. Or you can rely on other vehicles that interact with whoever you want to track to obtain this information. And you can extend this design in multiple domains. So essentially, when you move in a region where another domain is predominantly present, then you don't want to stand out. You don't want to be the only one that has credentials from your home domain. So you request a ticket that will allow you to address one of the local PCAs and obtain credentials like the ones that everyone else in that domain has. So you don't want to be like a fly that fell in a glass of milk, right? These credentials, as you obtain them, essentially could be seen as some sort of fuel, right? So your role, you need to be authenticating all traffic, you need to be using all these ephemeral credentials, and the question is, how do you get them? Can you get them for the 80 years of the lifetime of your vehicle? That would be extremely expensive, and we already had some, I'd say, a good argument about spending too much energy about all sorts of computations. Of course, this is less severe. So we advocate some sort of on-demand acquisition of credentials. And there are different policies. You can basically know how long you're going to drive, or you can do your best guess and get for a period, and then before you run out of credentials, you get a few more, and so on and so forth. There is one problem with this. The times of requesting these credentials and the lifetimes actually could be some sort of fingerprint. Someone is observing, or even the PCAs themselves, these curious authorities, could basically be using just timing information to basically track a given vehicle, right? So the proposal here is to essentially get everyone talking to a PCA to be aligned according to the clock of that PCA, and essentially get, well, I don't know, yeah, get credentials with lifetimes that are basically aligned the same way as they are for everyone else. And then this makes the anonymity set equal to the number of vehicles registered with that PCA. Now, what is this paper doing? Essentially, it's basically defining all the protocols of the vehicle to the VPKI or intra-VPKI interactions. It implements and it basically evaluates and analyzes how well they perform. What's the end goal? The end goal is to basically figure out whether this is doable, whether this is practical given what we have in our hands, and whether this could be an impediment for deployment. So I will quickly go through these protocols. I already gave the gist of how it works, but let's try, and I will just pinpoint a couple of interesting technical points in each of them. So here you see basically the interaction of the vehicle V with the long-term certification authority. It requests a ticket. It's a service granting ticket in Kerberos parlance. And you see there that the identity of the PCA, it's going to, oh, sorry. Yeah, I don't know. I think it will never work. Yeah, the identity of, okay, up here. The identity of the PCA it's going to obtain the credentials from is hidden from the LTCA. Nonetheless, then it obtains this anonymized ticket, digitally signed by the LTCA, which it presents to the PCA at the bottom part of this figure, along with a number of certificate signing requests, which are essentially the requests to get certified those anonymized public keys, the pseudonyms. The LTCA grants the service if the ticket is valid. And then you see that in the original requests for the ticket, the period for which the credentials are requested is given with these two values, T sub E or T sub S, while when the vehicle requests the actual credentials from the PCA, these values are actually different. They are within the broader requested interval. So this is basically hiding the information of when these credentials are to be used exactly, right? Now, this is the pseudocode, but we won't even bother. One point to make here is that there is a binding during this process between the ticket and the issued credentials. Why? Because this will be later necessary for the resolution of the certificates of the pseudonyms, essentially. If you want to figure out who was eventually behind a given set of pseudonyms, a given set of communications, actions, if you wish, within the vehicular communication system, you need to ensure a correct operation on that front. You don't want, in the end, even a misbehaving PCA to lie about that. And then the same, okay, this is the second part of this is the other protocol. So essentially here you have a binding of the long-term certificate for the vehicle to the ticket, and there's a different binding between the ticket and the pseudonyms to come afterwards for the resolution purposes. One could look exactly at the same type of functionality once you move to a new domain, a foreign domain. First, you have to figure out what's the how to say, the authority, the certification authority to address within that new domain, this foreign LTCA, and then, and this is true also for your home LTCA. Let's say you are a vehicle that is moving around, or for the PCAs, you need to know where are these certification authorities. And then the idea is that you first request a ticket from your home LTCA that will allow you to address a foreign LTCA, and then again repeat the process. Once you get a ticket, now you can address one of the PCAs which have a trust association with that foreign LTCA and get your pseudonyms, like everyone else in that domain. I'll skip the slide about revocation and resolution. I already mentioned this. So this is a summary of why things work the way I promised. So I mean, rather than going through this, you're welcome to look at the paper and let me know your thoughts about this. Now, let me say a few things about the experimental evaluation. And so we have a testbed which is pretty modest if you think about how each of those PCA or LTCA entities is running. And we want to basically see how they would behave should they face a realistic workload. Now, how do you get such a realistic workload? Unfortunately, we don't have a vehicle-to-vehicle or vehicle-to-infrastructure system deployed out there. So what we do is that we take mobility traces from two data sets. One is the whole country of Luxembourg. That's not such a big country, but that's where we have available traces from. And then the other one is from a city in Germany, Köln, and we have different policies, and essentially we emulate how these vehicles basically would interact with the VPKI. And then we run the vehicle functionality on a virtual machine and the PCA, the VPKI infrastructure, and a set of virtual machines. And we basically measure how this performs. Essentially, we stress the VPKI in order to see whether even with these modest resources it can do the work. And here you see for different policies what are on the y-axis the average delays to obtain credentials for the two data sets. And you see different, of course, behavior because there is dependence on the actual system, the actual mobility, the number of vehicles you have, the duration of the trip, the parameters of the policies, and so on and so forth. But the bottom line here is that if you see these three last bullets down here, you see that the likelihood that the delay to obtain your credentials is larger than that given value, which is, let's say, 167 milliseconds or 80 milliseconds or 74 milliseconds, or no, the probability that the delay is below that value is 99%. So this means that in all likelihood, you will get your credentials within a very short delay. And if you were to make the setup a little less stressful for the VPKI, if you were to, for example, request pseudonyms with a longer lifetime, and let me remind you that the shorter the lifetime, the shorter the period for which you are temporarily linkable, thus the higher the privacy protection, then you see that in the end, this delay flattens out really fast. So, and then the difference is not huge. Huh? If you were to look now at how well you utilize these credentials, well, different policies, these are all on demand and they all perform well. So we can basically confirm this from this figure. And if you wanted to see which of the two parts of the functionality is more expensive, clearly the ticket provision is extremely fast, the order of a few milliseconds, while the provision of the pseudonyms is the more expensive one. And here you see cumulative distribution functions for different parameters. And even though I didn't discuss this, here there is, let's say, a breakdown of all the operations with all the intra-VPKI functionality in order to resolve a pseudonym, meaning figure out what was the long-term identity behind one or more of the temporary identities, temporary certificates, and public keys and the corresponding private keys with which you signed, and essentially evict the entity from the system, which can be removal of the short-term credentials, but it could also be revocation at the level of the LTCA. So when you request next time a ticket to obtain credentials, then the LTCA can also say no. Some comparison here with respect to let's say various implementations which are out there. These are all research-oriented implementations, I have to say, and our code is not production level. We are improving, and then now we have it in the next generation, which is essentially the order of a few milliseconds per pseudonym, essentially. So, but this is not the point. The point is, oops, oh, there's a little bit of, the point is that essentially, even though in the community, it has been considered a major impediment, a very difficult problem to address. There were many questions about whether it would be, practical, deployable, or not, or too expensive. We figured out that even modest workstations running the PCA and the LTCA servers can handle tens of thousands of vehicles through typical workloads, even if you have relatively high degrees of privacy, meaning you are partially linkable for 30 seconds at a time, no more than that. Now, there's more to be done, there's more ongoing, so depending on how much time we have, I can walk you through, or the work is on the slides. For example, a little bit about the distribution of revocation information in these systems. You can use such a system in a different context if you want to protect privacy in a location-based service context, and of course secure this functionality. And there are common ideas, but with more freedom if you wish to apply them, exactly because there is no standardization effort ongoing in other large-scale mobile systems, for example, participatory sensing systems. Now, how much more time do I have?
Well, I think that it might be good to get some questions and see what people are interested in anyway, but we have plenty of time.
All right, okay.
Okay, but I think it might, I'd like to ask you a question.
All right, absolutely.
But, so we'll get a line up at the mic, and then you can go into some of the wrap up as well. How's that sound?
Sure, okay, two
Okay.
waves of questions.
All right.
Yes, please.
I'm Max Pala, Cable Labs. One question, have you considered, so all the times that you reported here are for signature generation, I expect?
Well, it's for the whole execution of the protocols I showed you, essentially. Many signature generations, if you're talking of the CSRs, many signature verifications and so on and so forth.
But it doesn't include, network.
So
delays.
yes, so the network delays here, exactly because they could vary depending on where the vehicle is and how the vehicle is connecting to the VPKI, are basically dwarfed in these measurements. And this was on purpose because you could be connecting to the VPKI through a roadside unit, and then you are subject to all congestion that this is facing. You might have a special deal with your telecom provider and you have a 4G network and so on and so forth. Or you might be in your garage, in your home network running. So yes, so all these numbers, if you wanted to see how they would be in real life, you have to add a few hundreds of milliseconds depending on what is the network that is connecting you to the VPKI. So this is pure processing and communication.
Okay.
Yes.
So another question that I have for you is, from what I see, and I'm sorry I didn't read the paper, but from what I see, you use like normal CPUs to do this signal generation. In many PKI environments, especially when you have CAs or authorities that have some stricter requirements around protecting the keys, you usually needs to use some HSMs or hardware security modules. And unless you're willing to spend very high amount of money for each of these PCA and long-term CAs, the performances are not nearly as these.
Right. So
have you
yes,
look
go
at
ahead.
the economic aspect of this,
Right,
and how to address that?
So actually, okay, it's interesting that you mentioned this because for many years, and actually the project I mentioned earlier, the need for an HSM or hardware security module has been, let's say, strong on the vehicle side actually, and in the project I mentioned earlier, this Preserve, essentially, actually we had an ASIC that wasn't, the best ASIC you could possibly think, but at least for the vehicle, exactly because there you have stringent crypto processing requirements. You have to validate, let's say, hundreds or thousands of signatures per second, unlike the loads that you are dealing with here, which are several interactions per several minutes, let's say, and so on and so forth, right? And we had an ASIC that can do up to approaching from below 1,000 signature verifications per second, right? There's much better hardware nowadays out there. So, yeah, absolutely. Yes.
Just a small note. I would suggest to look into two things. The first one is ASICs are usually almost impossible to certify according to some standards because of the protection of private keys. But for the vehicular, probably you can go around that. On the server side, I would suggest to look into bursts of requests, because that's where problems arise. If you don't have enough capacity, the delay becomes unacceptable, and you might incur into problems there.
Well, excellent. Thanks very much for the suggestion. Yes.
Hi, I'm Apostle Vasilev with NIST. Your protocols do depend on accurate timestamps. So to execute correctly, right?
Yes,
where do
correct.
you get the time from on both sides, and how do you deal with time drifts, let's say in the vehicle, if the clock is aging or is being influenced somehow improperly to drift away from the accurate time?
So for the hardware security module, for example, you have a real-time clock which you have to basically synchronize with an external source, right? One easy way to go about it is to rely on GPS or Galileo, right, for obtaining time. Of course, there is a set of constraints there, whether someone could try to spoof your GPS signal and so on and so forth. So we have a different part of our work for several years actually dealing with securing the positioning and the time synchronization for GNSS in general. For the servers, I suppose what we can think of is, let's say, NTP with the security, I'd say, add-ons that one can think of, right?
Well, NTP is not necessarily a secure protocol, right?
But for example, let's take let's think of what would happen here should you, let's say, should your clock is slightly not in sync with the clock of the PCA, right? So you appear and you request a bunch of certificates whose now lifetime will be according to the clock of the PCA, right? Depending on where your clock is, I mean, the PCA will decide which batch of certificates to provide you. Now, when you start using these certificates, if the clock of another car has drifted away from your clock, for example, it was in an urban canyon, it didn't manage to get the latest connection to the GPS and so on and so forth, then there are two things that can happen. One is that, okay, well, the drift is not severe enough, or if it is, let's say, such that it, for example, it rejects a given message because it looks at the certificate under which it is signed, and then that is already expired, then that's the worst thing that can happen. Essentially, you reject some of the traffic because you think it is outdated. It comes from a non-valid
right, but
certificate.
That's a sort of sensitive message, like an accident has occurred that could be a trap to somebody to really influence a chain crash in that way. So that's an attack pattern in a way, right?
Right. Of course. There's a whole area of work that is trying to look, and I have just one slide towards the end of the add-on work, where it's trying to look at the validity of the data itself, be it position, be it any sort of measurement. Now, the reality is that in these systems, actually, you have much higher, much more severe unreliability factors, in the sense that the communication itself, exactly because it's very simplistic in its nature, it relies on redundancy. So you have lots of messages being lost. So essentially, what you're saying has to be dealt with at the level of designing the application. What is your application for collision avoidance? This is where you should put enough redundancy and enough controls in your protocol to avoid, let's say, or to basically be able to filter out, manipulated, forged messages, or messages which are not forged, but it is what I call an input controlling adversary. Essentially, you induce a given value, time, location, etc., on a given vehicle, then everything else starts breaking down. exactly because there is no cross validation for those messages. So this is the direction one should go to deal with it.
I mean, I totally agree. These are difficult problems, but I'm not sure it's okay to kick the can up to the application developers if the problem can be solved at the protocol level, so that you give them a solid building block to build applications.
Absolutely, but you're talking about which protocol now?
For how to deal with the drifts and the tolerances that are involved in dealing with drifts in order to design a robust application.
Oh yeah, of course. I mean but this we're talking about the same thing. And what I was trying to make a distinction from is, one is the provision of the credentials, and then it's a whole ball game. Being an internal, let's say, adversary, how you deal, or being an adversary that is actually manipulated by an input controlling adversary, how you deal with, faulty information in whatever is a distributed protocol you are running. Yes.
Okay. All right.
No? Yes.
So I want to inject my question now, and then we'll get to the other three, which is, this would be a really, really big and very dynamic certificate system. There's nothing like it in the real world now. Are we going to have something like this, and is it going to actually operate the way it does in your test bed?
That's an excellent question. So do we have anyone from a car manufacturer here? Do you have anyone that works for a certification authority that is already investing in this area? No one?
No,
Okay.
we know they're around, but they don't come to IETF. So.
Yes, they don't.
Yeah.
So, I mean, the hope is that unless we have such a system in place, the rest of the gentleman who just sat down, that is actually, rightfully concerned about the security of every single protocol, right, that deals with all aspects, won't be deployed. So what we are trying to do with all this work, all these years, is exactly to show that it is complicated, but keep moving forward and demonstrating that it's not too hard in the end, and it's not too expensive in the end. So we should start, moving forward the deployment of such systems. And it's absolutely correct what you say. This kind of PKI essentially will be dealing with 5 or I don't know, even more orders of magnitude, more numerous credentials than any other PKI we have seen so far. So this is something that we have to address as early as possible, because the flip side would be to have a toy system out there that says, well, I can provide you with very few credentials. But then that would be at the expense of privacy protection, for example. So we don't want this. We want to have both.
Yep. Okay.
Morning, my name is Saulo from the International Civil Aviation Organization. In your analysis, did you consider also the speed of the vehicles, because you are exchanging information between moving targets? Is the speed considered as well? And if you can expand this to higher speeds like 500 knots instead of 8 kilometers an hour?
Aha, okay, interesting question. So yes, absolutely. So I'll show you a few more slides later on. These are real mobility traces. So this is how fast you move on a highway, or how fast you move within a city, right? So velocities change, right? And this is taken into consideration. Now we're talking about the interactions with the VPKI. There's a different line of work where you deal with the reliability of the communication with this unreliable broadcast, which is the de facto primitive in these networks, or other multi-hop communication. What I cannot tell you is whether this would work. Not this. The provision of certificates would definitely work, right? What would not work? What I cannot tell you whether it would work or not is these protocols for example, unmanned area vehicles, or I don't know, helicopters or soldiers or airplanes and so on and so forth. But there's a great commonality there. I mean, I guess one has to do the homework, right, and deal with the exact parameters of the system. But when it comes to interaction with an infrastructure, it depends what's your communication link to that.
Yeah, because one of the factors you mentioned is collision avoidance. It's one thing is collision avoidance between two cars moving 80 kilometers an hour. Another thing is 500 knots.
So, absolutely.
So totally different.
So this actually gives you an opportunity to mention another kind of work, another part of the work we're doing, where we take the standardized, let's say, ways of communication, and then we say, okay, we need to have the security I discussed before. We need to have privacy. You need to have this whole deal, right? Still, even though you add crypto accelerators, at some point all this is tedious. So how can we, for example, offload the vehicles from the verification, let's say, onus, and at the same time maintain security? And one approach we are pushing forward is some sort of collaborative verification, where I verify a bunch of those messages, but then I piggyback in subsequent submissions of mine some sort of information saying which of those I verified. And you, if you believe me, you can use that. And all of a sudden you save yourself a great deal, and you can scale to a larger neighborhood. But yes, absolutely.
Thank you.
Cheers.
Yeah, thank you. So here's Guilin from Huawei International. So I have two questions. The first one is that from your presentation, I feel that the key idea for your system still use the long-term certificate and a short-term certificate. But basically, this idea, I think, should be the same as the DSRC, or formerly it's called the IEEE 802.11p. You must know this one. So my first question is that, what's the difference between the system proposed by your team and the DSRC?
All right. So the question is, how does all this, let's say, can it be positioned with respect to standardization efforts? So first thing I should clarify is that 802.11p is a modified medium access control protocol with a different physical layer and a multi-channel operation targeted for and all sorts of adaptations, let's say, for the vehicular communication environment. Security per se is not addressed in 8.11 or DSRC, which is the predecessor of 8.11. There's a totally different version of DSRC, which is, was used for, how to say, toll collection, but that's ancient history. Now, security, from the standardization point of view, from the IEEE point of view, is addressed in a working group and a document called the IEEE 1609.2. Okay, so there, they use the same ideas. Actually, the effort of 1609.2 started later, after, let's say, our efforts, and I provided to them, let's say, feedback in the olden days, and we're still in touch. There's a basic difference there. There, they provide the vehicle with the whole set of pseudonyms for the lifetime of it, or for several years. And essentially, they use a crypto mechanism that essentially, on a periodic basis, enables the vehicle to use the corresponding credentials, the corresponding private key. And this goes a bit against this on-demand provision, and it incurs a much higher overhead a priori. So think of a vehicle essentially that you drive from your home to your office and backwards 2 hours per day, but then you have credentials for 22 more hours, which you're doing nothing with, right? That's the thing. And then there are a number of other technical differences. And there are, for example, other issues such as the distribution of revocation list, which they don't address, and so on and so forth. So it's a parallel effort to which we contributed. They chose a different approach, not this on-demand provision. I mean, I don't want to comment too much and say, well, we are much better or anything like this, but there are pros and cons, let's say, that one could argue about. The paper discusses in detail how this work, let's say, relates not only to the 1609.2 but other research proposals. So I would suggest take a look. The key differences is what I described here. And let me know if you have additional questions. I'll be happy to enlighten you more.
Okay.
Cheers.
So second question is that I would like to know a little bit more detail about, because here certificates are used, long-term or short-term ones. So my question is that, could you give us a little bit idea which kind of signatures are used here? And also, what is the key size?
Aha, excellent. So
common key size.
Absolutely. So there, exactly because we were also in touch with an organization which is not a standardization body, but what you call a harmonization body. I mean, that's what you call the car-to-car communication consortium. Essentially, there was a consensus that the key lengths should be, I don't know, the order of 256 bits, right? Now, the second point where there was consensus in the community was that these keys, even though they are ephemeral, they shouldn't be very short. So basically, you shouldn't be able, a year later to basically rewrite what happened should you have a transcript of messages, right? Because if you could now break the key and then recalculate signatures and so on and so forth, that would be dangerous. There's an issue of liability and towards a liability attribution in the physical world that is lurking behind us. So that was the motivation for the key length. The second dimension was that communication is at a premium. So essentially, being over a channel whose bandwidth you cannot control and grow, you have to keep the cryptographic overhead as low as possible. And among available, well-understood cryptographic primitives, elliptic curve DSA was the one that provides,
RSA,
compared to RSA, for example, even though RSA would be much more, favorable in terms of very low verification times. Nonetheless, so here it's ECDSA 256, and this is, let's say, also in accordance to the IEEE 1609.2 standard.
Thank you.
Yes.
Right. Amelia Antasdotter from Article 19. So I have a question. Isn't it true that the CA will actually have all of the information from the sensors and about speed and about timing, that whoever issues the certificates will know everything about the vehicles that is protected in the privacy model otherwise? And the reason I'm asking is because I understand from a consumer perspective the challenge of kind of vehicle to vehicle or vehicle to other things situation to be that there's a big competition for driver data, how to lock them into specific insurance schemes, and perhaps also safety measures from public authorities and so forth. So it seems to me as long as you have this central location where all that data is somehow generated or stored, you're not basically solving tricky problems for consumers or addressing privacy fairly well.
All right, so let me try to rephrase the question for everyone to understand, and then you let me know if I got you right. So the question is, in such a think of the car as a huge sensor, which allows you to basically learn too much, huh? even better than what your mobile phone nowadays does, right? So what about this data? Well, the quick answer is that none of this data, and even less, not even who you're going to address to obtain your credentials from, is communicated with any of the entities I described here. What you're referring to is a different problem that says once you have credentials, let's say, yes, or if you forget all this provision of credentials, if you think of the reality now where you are a car manufacturer and then you tell your clients whenever they sign and they buy a car from you that they also allow you to collect all sorts of diagnostic data about the car and everything else. This is a problem that you have to address exactly there. Now, the question to ask would be, if you live in a world where all this data anyways, for one reason or another, are at the disposal of very curious entities, why would you bother building a strong privacy-preserving and security-providing system like this? Well, the answer to that would be leverage legislation, make sure your users are well aware where they're signing from, and keep them away from signing up for such deals and protocols that basically give their data away. Otherwise, of course, this is futile. Eh? So resistance is futile if I'm trying to advocate such a system while the data are going in anyways.
But then who do you imagine to be the CA in the system? Like which?
So the CA could be you. I mean, might be an excellent business opportunity. You're the CA who sells basically, but no, I mean, let me be serious here. The CA could be the Department of Motor Vehicles, right? The Ministry of Transportation, depending which country you are, a municipality. Or it could be any CA that, now perhaps there is a differentiation between long-term and PCAs. A PCA could be any certification authority in the world now that sees a new opportunity to sell certificates for whatever price. But I mean, I'm a researcher. I mean, if you want me to put my entrepreneur hat, I mean, we can have a different discussion, but we can have it offline. But the question who is essentially will step forward and instantiate the CAs is open. It is likely that the car manufacturers themselves might be the ones, but it's also possible that.
So because that's what I thought.
Yes.
So then if the automobile manufacturers are the CAs themselves, then this model would aggravate the problem of data sharing for consumers because they'd have both technical leverage and contractual.
So yes, but this is a hypothesis, let's say, which we don't know yet. Essentially, the whole underlying principle of designing such a system, and you will see it in the other systems I'll show you, is that you have a separation of duty. And then, of course, if all these entities are run by the same entity and it has the same gluttonous appetite for data, then eventually you cannot do anything. But as long as these entities they operate according to specific, let's say, legislation, and they're run by different entities, then even if they colluded, then what we do, the only thing we can have is that the design is there to reduce as much the exposure as possible. Then again, look at the system. The only thing you know is that if you're the LTCA, that I'm asking you for a ticket, nothing else. What you need to do next is to go out there and collect tons of data from the wireless domain and then try to make sense of what's going on. If you make me sign up to provide you all the data, that's a different story. But I won't accept. Okay. What am I going to do if I like the car? Well, I don't know. I will be in a dilemma. I will tell you then.
Okay, thank
you. For the time being, I don't know. Yes.
Hi, Max Bala, Cable Labs. A small question, consideration about what you say for key lenses, etc.
Yes.
The whole system is based on the assumption that cryptography is fast and can be done fast and is small in sizes, right? You have requirements about sizes because of the communication, etc.
Sizes for what, if I may ask?
Sizes of signatures, for example, on certificates to be, for validating, etc. One of the things that it seems we're going that direction. There's a lot of research going on about, quantum resistant cryptography. And what we have today is definitely goes in a completely different direction. Signatures in the order of many, many kilobytes, key generation that takes a long time, stateful or stateless. Stateless even adds more in the size of signatures, etc., which definitely are not compatible with this system. Have you considered how the future of cryptography, since these are long-lived systems, because P256, for example, will not probably withstand the test of time. We're thinking between 5 and 10, 15 years, which for such a system is a very short time.
Yes,
so have you considered how in the future you will try to address this problem, or how your system can be parameterized so that you can also accommodate, especially probably from the vehicular, from PCA, very short-lived credentials, might not be such a big problem unless for auditing purposes, as you were saying later,
right.
In a year you can still do some damages, but for CAs and PCAs, that might be a big problem today, especially if you invest a lot of money.
Absolutely. So I think okay. So essentially, I think that we already have this common point that it depends actually what you expect. What's the lifetime of the data which are digitally signed, let's say. So if you want to use them for a posteriori, let's say, liability attribution and so on and so forth, 10, 15 years after a collection of a transcript, let's say, I'm assuming you run some sort of black box on board.
Also consider the long-lived credentials and credentials of CAs.
Exactly. So one thing you can do is that, for example, you can increase the key length for the long-term certificates while you keep the ephemeral certificates with this 256-bit security, or you can keep increasing, right? I mean, but then you have to choose a crypto system that doesn't blow up the communication overhead. Regarding the quantum, how to say, proof future of cryptography, I'm not the right person to comment. I mean, you have to find people in the room who are cryptographers and tell you. I have talked to people who are looking at the problem. So far, it doesn't seem that we are in a dire situation. I mean, so that our crypto is broken tomorrow. But again, I mean, don't ask for I can only give you an educated guess on that.
So come to Cypher G, because that is on the agenda and some of
However,
this stuff.
I just
But-
want to point out,
Yes.
because of the deployment requirements, right,
Yes.
this will take years to deploy.
Yes.
By the time that we are ready to deploy such a system, we might have to change it.
Sure.
So I would suggest.
This is an excellent point. So let me add to this. Essentially, one should be very much concerned about how to update, for example, the crypto primitives that run on board the vehicle, and how would you support them, right? And then this goes into the direction of how do you handle software updates, and how do you do them in a secure manner? Let's say maybe this involves recall of the vehicle to the manufacturer and so on and so forth. I don't know. There are more issues that, if you think of the lifetime of a vehicle, which is in the order of 10 years, then
The other
we
thing,
have to.
sorry, for the anonymity, pseudonymity, etc.
Yes.
I do understand that, you know, the electronic world is a different than the physical world.
Yes.
But today, vehicles are required to have a very strong, long-lived identifier, which is the license plates.
Or the VIN number, yes?
Or the VIN number,
Yeah.
right? Have you considered using that, because that's already out there, is already used as an identifier? Privacy concerns there, as far as I know, have not been addressed. So why are you trying to address something that is not addressed today?
Well, so my take on this in general is that if you introduce a new technology, what you want to do in the end is that you don't want to introduce new vulnerabilities or new problems that were not there before the advent of this technology. And in this case, if I go around and I beacon about my location, and if I provided my long-term identity with every beacon I send out, my VIN number or whatever it is, then I would create a much bigger problem than the one that the garagist basically can look under my hood and see my VIN. That's essentially the mindset. So there's always a before and after of a new technology, right? So if you introduce a new one, make sure you don't create a bigger mess than the one you had before.
Okay, thank you.
Okay, let's thank our speaker for ending on, especially on a principled note. And let's see, I have just one last thing for you guys, which is, this is us. We'll see you again next time, where we're skittering on top of a screen. But thank you for coming to the IRTF Open. I'm happy to have any last questions, or you can come up and talk to me while the photography is happening for the award winners. And we'll see you in the RG the rest of the week as well. So see you later. We're giving you extra time. You can have 20 minutes back before lunch. So I think speakers should come up, I guess, right, Matt? We have some certificates for you. It's really hard to actually have a good conversation. We just turn off the, just against here. I have it on my, I can make a big slide. Sure, hang on. You should tell Panos to come up though. You don't want the cat? How about just in front of the oopsie, that was dumb. I can't put something else on me that go, yeah. Hi. Yeah. You talk, you write a charter proposal. You speak to me. You speak to the IRSG, the other members who are already there. Usually we started a mailing list pretty readily, so you can start talking to people about it on a mailing list, and we see what the traction is. So if it looks like a lot of people are interested and the charter looks promising, then we can come up with a proposed group that can run for 3 times, and then see whether it's going to be long-term or not. Is there a topic you're thinking about? Or?
Yes, this work that system kind of just presented. We have seen the issues like
Yeah. 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 Okay.
And that's why.
Yeah.
I can say no problem. What you're telling me, you have to go for the chair.